So we're just going to review that. Really important for this topic. So in this topic we're learning about group 1 alkali metals, group 7 halogens, and we'll go on to learn about the transition metals today and noble gases, and I'm going to go through those with you. But it's really important we can keep going back and we're practicing stuff. And alkali metals, you told me at the start that sodium is more reactive than lithium, and I was looking to see your answers. I was walking around, many of you had this stuff tick as you go. So first of all, did you say that sodium and lithium react by losing one electron? Just put a tick on your page if you had that, or put a cross if you didn't. Losing one electron on your mini whiteboards. Put a little tick or cross, and we'll tot them up in a minute. They both react by losing one electron because they're both in group 1, right? Both got one in the outer shell. And so, for example, lithium atom will turn into a lithium ion. And we'll review this again when we go through the bonding test in tomorrow's lesson, or next time I see you, rather. So, and they both end up forming a 1+ ion, which is why they're in the same group. You said to me, some of you, or you wrote down, some of you on your boards, that sodium reacts faster, which means it must lose its electron more easily. But let's think about why that's happening. So you had to say for that, sodium has, or Na has, one more shell. And some people write in their answers, or I think wrote in their answers, they have one more outer shell. You can't have, did anyone write they've got more outer shells? Good. Well, sometimes people do. You've just got one more shell, only one outer shell, isn't there? And so that outer shell is further from the nucleus. So outer electron, or if you like shell, is further from the nucleus. So it's a tick for that, tick for that, tick for that. 3 so far. Show me with fingers how many ticks you've got so far, please. You could have also said there's more shielding. More inner shells means more shielding. And that shielding is the inner shells between the outer electron and the nucleus. Another tick there. But the point is, the key point is that there's less electrostatic attraction between the outer electron of sodium and its nucleus than for lithium. So less electrostatic attraction between outer electron and nucleus. And then the last point you certainly need, so less energy needed to overcome. And so that means it reacts faster. Oops, overcome. Right, so that electron is lost more easily for sodium, so you get a faster reaction. So there's quite a lot of points there. 1, 2, 3, 4, 5, 6. Show me with fingers how many points you've got, please, everyone. The transition metals, you don't need to know loads about these, if I'm really honest. And if you just kind of do a very rough sketch of a periodic table, something along these lines. This section here, at least as far as you need to worry about for GCSE, this section here is what we call the transition metals. You're expected to know roughly where they are on the periodic table. And when you think of metals like iron and copper and silver and gold and tungsten that you might come across in daily life, and palladium and platinum that maybe some of you have heard of, or chromium, that's probably where the metals are going to be. And they are distinctly different in many ways from this section here, which of course is where the alkali metals are. There are some big differences between these metals and these metals. Now, these metals behave like you assume kind of normal metals do in many ways. Right, so we're going to go through each of those points. And what we're going to do is we're going to fill in a kind of Venn diagram of transition metals versus alkali metals. So what I want you to do, and I'm going to show you a couple of things when we're doing this, you're going to have this sheet, and I want you, don't bother filling in the sheet right now, but I want you just through discussion to highlight which of these you think are alkali metals. So just put ticks next to the ones you think apply only to alkali metals on that sheet, please. If you're still writing notes from before. There it is. I'll leave that right. So, which of those sentences apply to alkali metals only? Think about that for a couple of minutes, and then we'll discuss it. So, that section there that I've coloured in is where the transition metals are, as far as you need to know. There are some within that shaded area that we learn at Key Stage 5 are not technically transition metals, but worry about that in year 13 or something. So, but that section there are the transition metals. Which ones are alkali metals then? So we'll just go through those together now. Those ones I've ticked there go in the Group 1 metal section only. Okay, so can you just fill those in here? I'll do the same with you. So can you put in low melting point? You can shorthand it a little bit. Stuff you know already, very reactive with water especially, but oxygen too. White compounds, I'm really emphasising the point these are compounds, and I'll get you round the table in a minute and we'll look at some transition metal compounds which are not white. They're soft, and we know that from our demo last time, and react with water. And you don't need to elaborate on that, you know that stuff. Forming H2 maybe. Fizzing and floating, all the stuff we've talked about before. And then form 1+ ions, that's because we're in Group 1. So they're the things that apply only to alkali metals. Once you've done that, can you go through the list again and put a cross next to ones which you think apply to all metals? And we've talked about metallic bonding in the first topic, or the bonding topic. Which ones of those statements there apply to alkali metals and transition metals? Yeah, so those things, the fact that they form ionic compounds and they're good conductors of heat and electricity, are things that apply to all metals due to their kind of, metals are things that form positive ions really, and they're good conductors, and we need to be able to explain that like we did in the metallic bonding lesson. All the other things there on the list, so high melting point, good as catalysts. We'll talk about this in a sec without the video on. Good catalysts, coloured compounds, strong and hard, high density typically. These are, as we discussed as well a moment ago, these are general general things that are not necessarily true for all of them, but many of them form different charged ions. And that's confusing because it's not obvious. Based on everything I've told you so far, you'd think, well, Group 1 they form 1+, Group 2 they form 2+, transition metals they do all sorts of stuff, right? So I'm going to talk you through a couple of those bits now, and then I'll show you a few things. So there's quite a lot here. This is about all you need to know for this entire section of the topic. So you need to know these things. So all I'm going to say is learn them. And they won't necessarily ask you directly, what is it about transition metals, eh? They won't do that. They'll say to you, which of these compounds is coloured? And they'll give you a bunch of compounds, and one of them will be a transition metal compound, for example. So, a couple of things then. The high melting point, well, that's for all the reasons we talked about when we did metallic bonding. I'm not going to spend any more time on that. It's just that, and the reason for that we explore much more at IB or Key Stage 5 level. So let's not worry too much about that one. They've got typically high melting point. Some not so. The mercury's about there somewhere, and so, or there somewhere. And so that, it's not entirely true for all of them, but generally speaking, they've got high melting point. We will learn that catalysts are things that increase rates of reaction without being used up, and it just so turns out, because they can form different charged ions that make good catalysts, we're not going to do any more on it than that for now. But you've heard, I think, of catalytic converters for cars, right? So in an exhaust pipe of a car, you've kind of got this honeycomb structure at the back end, And in that, they've got sprayed onto the honeycomb structure. You've got transition metals. You've got rhodium, palladium, platinum, these precious, expensive metals, which are in that catalytic converter. Those things get stolen sometimes, if you live in London especially, and those metals are extracted, and they're important because they catalyse the breaking down of waste products from the engine. So you don't need to know much about that, and we'll talk about it a bit more in the rates topic, but you do need to know that it's transition metals that are used there. They're strong and hard, fine, but let's look at the coloured compounds bit. So here are a bunch of transition metal compounds that I've got for you. So we've got one that's got, it's a compound made of iron on the left, a compound made of copper here. Just eyes this way, please. You're not going to see them like that, are you? This is a compound made with lead, lovely orange colour. My favourite colour of all, this lovely cobalt chloride, is a really strong purple colour. Copper sulphate you've seen before. All compounds, not the metals themselves, but compounds made of transition metals. So a transition metal bound to sulphate or chloride or oxygen or chloride or sulphate or whatever. But it's a transition metal ion in there that's giving it the colour, all right? And so you're expected to know that. It's an important, like, one marker that's going to come throwing at you at some point. The high density, fine. I'm not going to cover that in particular detail, except you need to know that they're high density. But one nice little detail for you is they form differently charged ions. So this is a question which you should know. I'll ask an extra hard question in a moment or two. But could we work out, please, the charge of iron in these three compounds? So bearing in mind that oxide is always 2 minus, what would the charge of the iron be in each of these substances, do you think? Have a little think about it, see if you can work it out. Let's not do that. So the charge on oxide in each case is 2 minus. So what must the charge of iron be in the one on the left? So you worked out this one, because you've got to have ionic compounds with 0 overall charge. So that must be 2 plus. Both of these must be 3 plus. So 2 3 pluses and 3 2 pluses make 6 plus. And as one of you worked out, some of you worked out, these must add up to 8 plus in total. So you can have 3 plus and 3 plus and 2 plus. That came up in the Year 11 mock this year, that exact question. You have to work out what the combination of ions were, of iron in that compound. Right, good stuff. So, does the excitement ever stop? After a little bit of fun there, a little bit of winding up, we're going to talk about noble gases. Noble gases. Noble gases are not very interesting, but quite important for your GCSE. So they are, and the word we need to use to describe them is inert, and you describe them as inert because that means they're very unreactive. And I'm going straight for the facts that you need to be able to state, and we'll talk about this in a bit more detail, and I'm going to try to get you to think a bit as we move on. So they're inert, they're unreactive. There's helium, which has got an electronic configuration of just 2. We've got neon, which has got an electronic configuration of 2 8. We've got argon with an electronic configuration of 2 8 8. And we're not going to worry about krypton and xenon and radon. I think the last one might be organoson, that's on the periodic table up there. But let's just worry about the ones that we need to worry about, so below the atomic mass of 20. Okay? Atomic number of 20, sorry. So helium's got 2 4, that's 20 10, and argon is 18 and I think 40. Okay? So that's how many protons and electrons they've got, 2, 10 and 18. Now, what you would say in an exam of why why noble gases are unreactive, I think is obvious, but then I've been doing this a while, so maybe it's obvious to me but not to you. So let's have a little discussion about that for a moment and see if we know. So, well done. All of you, I think, from the discussion you had there and the answers you gave, pointed out they have full outer shells. And we talked previously, didn't we, about the idea that other elements react, and when they do, they lose or gain or share electrons to become or to have full outer shells, or that's the outcome of the reaction at least. So if you mention that noble gases are unreacted because they have already full outer shells, you get a mark. The second less obvious mark that sometimes in exam papers would be around explaining why that's important. So I'll give you the short answer, then I'll give you the long answer. The short answer is what you write in an exam. The long answer is me doing my best to explain it in such a way that hopefully you'll remember it better. And because I want to push you a bit beyond the GCSE if I can. So full outer shells, they don't or they can't easily lose or gain electrons. Okay? Your 2 marks are there. You can probably move on intellectually if you want to. That's about it. And we're going to look at some other bits and pieces on this, but let's think about why there is. So what we're going to do with a little thought experiment, we're going to compare neon, which looks like this, with 2 elements that are adjacent to neon in the periodic table. So when I say adjacent, I mean next to. So neon's got 10 protons. Fluorine, which is next to it's got 9 protons. So it's very, very similar in its atomic structure. So we've got 2 in the first shell and 7 in the second shell this time. And neon is also next to, although it's in a different row, sodium, which has got 11 protons. So sodium, as you know, 2, 8. While I'm here, how many rows, which row of the periodic table is sodium in without looking at the periodic table? 3, 2, 1. Which row, which period, which row? So count the shells, in other words. 3, 2, 1. Let's try that again. 1. So it's got electronic configuration of 2, 8, 1, 2, 8, and what am I doing? 2, 8, 1, 2, 8, and 2, 7. What row of the periodic table is this in? Which period is it in? Try me again now. 3, 2, 1. Right, 3. It's third row, 3 shells. Group 1, group 7, group 0. Let's write our heading, let's change our heading a little bit to noble gases group 0. Sometimes written as group 8 elements. So they do not react, they exist on their own, they exist as individual atoms. There's some things about them we need to learn as well, but let's get our heads around the reactivity to start with. Now, what happens to fluorine electronically when it reacts, and what happens to sodium electronically when it reacts? Discuss that now. You all pointed out that fluorine reacts by gaining 1 electron. So neon that's next to it doesn't easily gain an electron. Let's think about why that would be. So to gain an electron, that electron can't fit in the outer shell as drawn. So there's actually more shells that are outside what we call the outer occupied shell that are empty. So if neon were to gain an electron, hypothetically, it would have to go in to this third shell. Well, why doesn't that happen? It can go into this second shell, and that reaction is quite favoured. We know that's a fast thing to happen from what we talked about the halogens, but why doesn't it happen for neon? It's all chemistry's really easy. I think some of you think it's really hard. It's really not. It's really easy, and it's all a big con that it's difficult, right? It's just the same answer every time. Think about the number of shells. Think about the electrostatic attraction. Think about the shielding and all of that. For sodium to gain an electron, for neon to gain an electron, have to go into the third shell, which is further from the nucleus. Less electrostatic attraction to the nucleus for that electron coming in. So it doesn't easily gain an electron. Sodium, on the other hand, does lose an electron easily, but neon doesn't lose an electron easily. Why doesn't neon gain an electron easily? Discuss that now, please. The point here is you're really only getting to is these 2 points. Fluorine gains an electron easily, whereas neon can't. Sodium loses an electron easily because neon can't. That's all to do with the fact where that electron would have to go, third shell, or have to be pulled from the second shell, and the electrostatic attraction in each case, all right? So I'll put that in brackets as the level of thought that will help you understand this well. There are some details about the noble gases that I want you to have those. So can we now flip to this page on our notes? So group 0 are these ones over on the right hand side, and they are obviously the noble gases. And the symbols, I'm not going to write them down because they're on the periodic table. The number of electrons in the outer shell we've already covered with 2, 8 and 8. I'm not worried about krypton, xenon and radon. And they're all gases at room temperature. Gas, 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 gas. The clue is there, the boiling point is below room temperature. They're all colourless. Don't worry about that at all, don't even know why that column's there. But what I do want you to know is there's a trend here. So what is the trend of boiling point, please? If you can work that out from what's given to you there. And this would be given to you in an exam, but we need to think about the reasons why. So what is the trend of boiling point, please? What you need to know ideally, you'll certainly be able to work out, is the trend. And notice it is a trend, and often in an exam what they'd ask you to do is they would not give you one of them, like they wouldn't give you the 190 there, and they'd say, well, what do you think the boiling point of argon would be, say? You'd have to give a number between -246 and -157. You have to interpolate, predict what the boiling point would be. All I'll tell you now is something we'll come back to, a bit more in a later topic, is that the boiling points, if you just add this please on your notes, the boiling points increase down the group as what we're just going to call they're not technically intermolecular forces here, but the forces between the atoms, or intermolecular forces we'll call them, intermolecular forces increase with larger atoms. So as the atoms get bigger, there are more electrons, and that means you get stronger intermolecular forces. We'll talk about that a bit more when we do the next topic, actually, when we do fuels. Right. So we need to know what noble gases are. We need to know all of this stuff that's here. We've just done the low reactivity. We've explained the low reactivity on our notes already. But you need to know some uses of noble gases. And for that, I'm going to show you a little video and mention a few things, and we'll write it up together. And so, other trend I want to show you, you don't need to know the reason for, is that the density increases down the group as well. And you can see that in data, and again, they might ask you to predict what the density is. But why are noble gases used in certain situations? So why do some food packets contain argon? And specifically here, we'd say something along the lines of, so it's unreactive. You might mention the full outer shell and all the stuff we talked about before. But there are some particular noble gases, as we talked about with the Hindenburg, that take advantage of either their low density or high density. So let's start off with, I'll do it on the notes down here. So helium used in air balloons, because again, unreactive, full outer shell, all that stuff, always the same. But you'd say here that it's low density. The idea is that having low density will allow it to get lift up the airship into the air, and the unreactivity stops it catching fire, like the Hindenburg did. So what happened with the Hindenburg is that as the Zeppelin arrived at the station, there was a static spark went from the metal sort of station that it ends up at to the Hindenburg, and that caused the hydrogen to catch fire. right? And lots of people died. And so they use, if they do things like this now, they use helium. For argon's got uses that take into account its density that's greater than air, about double the density. Hang on a second, let me think about that. Argon is slightly denser there, not quite double, but it's slightly denser than air. And so we use it for welding. Again, same answer every time. It's unreactive, and it kind of is heavier than air. And that's important because it can kind of act as a blanket and stops oxygen getting to the metal when welding is being taken place. So it prevents oxygen reacting with metals that are being heated. And we also use argon, noble gases, in light bulbs, filament light bulbs as well, to prevent oxygen getting there. But the idea of it being heavier than air is important because it kind of acts as a blanket and sits there over the welded metals. Okay. We also can sometimes use noble gases in fire extinguishing systems for exactly the same reason. But all you've got to get into the habit of talking about the full outer shell, the unreactivity, and the density. There's some more stuff over the page, but I'm not really worried about that, to be honest with you. So that is your kind of rapid overview of what you need to know for transition metals and noble gases. We'll do a little bit of practice now before we go.